Hello everyone. For this video, I'm going to do all of the homework questions from Part 2 of your Measurement Geometry 2 packet. It's due May 15th, and I'm going to do them all in order, so feel free to fast forward and rewind and watch again and again as you see fit. Okay, here we're trying to find for problem 1a, the surface area of a square-based pyramid. Okay, the surface area is going to be found by finding the area of that square, which is 8.5 times 8.5, times the lateral area of that pyramid, which is these four triangles. The area of this triangle is 1/2 times the base, which is 8.5, times the height of that triangle, which is the same as the slant height of the pyramid, 12.2, and we have four of those triangles, so that's where this has come. This is called calculator ready form, so you could go straight from here to here if you would like. I've put these in here to show you that this 72.25 is the area of the base, and the 207.4 is the lateral area of my pyramid, and added together you get 279.65. Okay, for problem 2a, they're asking for the volume of a square-based pyramid. Volume of any prism is just the area of the base times the height, but when you have a pyramid, it's just going to be 1/3 of that. The base in this problem is a square, so there's the 20 times 20 for area of that square. The height of that pyramid in this problem is 15, so that's where this comes from. And 1/3 times 20 times 20 times 15 is 2,000 cubic centimeters because we're talking about volume. Okay, this time we're given a triangular-based prism, and they want us to do the surface area. We're going to have to do a little bit of work this time. The surface area is going to be found by adding the area of the two bases, and the bases in this problem are triangles. So the area of a triangle is 1/2 base times height, so 1/2 8 times 6, and we have two of those triangles, so that's where this 48 is coming from. Now those are the base areas, but we need the lateral area as well. The lateral area is composed of these three rectangles, and the rectangles are easy for two of them, because we just have this bottom rectangle here, which is 8 by 18.5, that's that, and 6 by 18.5, that's the one on the side. But this big one right here, we don't actually have, we have the 18.5, but we don't have this measurement. Well, that's where the Pythagorean theorem comes in. So to find that side length, we're lucky this is a right triangle, so we can just do a squared plus b squared is c squared, and c turns out to be 10. So when we put 10 into this formula here for the area of this rectangle, we get 185. So what you get for the surface area of this is your two triangles plus each of your three rectangles, and you get 492 square centimeters. Okay, volume of a rectangular prism, they don't come much easier than that. Length times width times height, 8, 6, and 10, multiply those together. Or you can look at it the same way we do other prisms, which is the area of the base, which is 8 times 6, and just multiply by the height. That gives us our third dimension. So 8 times 6 times 10, 480 cubic. For number 5, they're giving us another rectangular prism. They're asking for the volume, which is just length times width times height again, 4 times 2 times 3. For the surface area of this thing, we basically have 6 rectangles. We have this 2 by 3 one that's on the bottom and on the top, so 2 times those two areas. We have a 2 by 4 rectangle that is the front and the back, so that's 2 times 2 times 4. And we have a rectangle that is the right of this prism and the left of this prism that are 3 by 4. So we have 2 of those. So total area is 52 square meters. For problem number 6, they give us a cereal box here, and they give us the base area because they give us the 20 and the 5 for the length and width, but they don't tell us the height. However, they do tell us the volume. So I know that volume, which is 3,000, is base length times width times height, and so we end up with an equation that looks like this. And now we can use our number sense and algebra skills and finish this off. How do you get rid of this 100 that's being multiplied by h? You divide both sides by 100, and height turns out to be 30 centimeters. Okay, in problem number 7, they're asking us to find the volume and surface area of some pyramids in Egypt. So if you take a look at this drawing here, volume is going to be really easy. It's always 1/3 base area times height, and since the base is a square, it's just going to be 220 times 220, and the height is given to us as 105 meters, so all we have to do is 1/3 times 220 squared times 105, and that gives us 1,694,000 cubic meters. That's a lot of volume. Okay, now surface area is a little more complicated. We have this square at the bottom, which is going to be our base area, 220 squared. The lateral area is going to be made up of these triangles. The problem with these triangles, we don't know the height of any of these triangles. And the height of the triangle itself is the same as the slant height drawn here in green of the pyramid. So in order to find that, we're going to need to draw this little right triangle to figure it out. So I've drawn that down here. And you can see the height of the pyramid gives us the height of this triangle. Okay, where this 110 comes from is the distance from here to here is going to be half the length of the side of a square there. So instead of 220, we're going to have 110 there. Then we use our Pythagorean theorem, and we get the slant height to be 152.1, which is going to be the height of each triangle. So when I put it back into my formula, each of these triangles is going to be 1/2 220 times the slant height, 152.1, and there are 4 of them. So 4 times the area of one of those triangles, and that gives us a total of 115,324 square meters. Now it is debatable probably whether or not we really need this base area for the pyramids, but if we don't include the base area, then that surface area is going to be this. If we do include that base area, which is on the ground, and therefore it's maybe debatable whether or not it counts it towards the surface area. Okay, if we do include it, then we end up with 115,324 square meters. Okay, in number 9, we're trying to find the volume of this hexagonal prism, and we haven't had to do anything like that really, but the nice part about it is all volumes for prisms are the same. It's the area of the base times the height. They've actually done a lot of the work for us. They've told us the area of this base is 40 centimeters squared, so I don't have to do any calculations to find that area. So all I really have to do is do 40 times the height, which is 26, and that gives me 1,040 cubic centimeters. Now, the problem is the question is asking, can this hold a liter of milk? Will the pitcher hold a liter of milk? Well, you just need to know that 1 liter milk is equal to 1,000 cubic centimeters, and we got 1,040, so we should be okay with this pitcher. Okay, so for the problems on 447, now we're looking at cones. So we're looking for the surface area of this cone, and the cones will set up exactly the same way as pyramids do. There's one base, and then there's a lateral area. The lateral area, though, is going to require the slant height, which is that distance from here to here along this edge. So the base area is just going to be a circle every single time, so we're looking at pi r squared, and the lateral area is pi r slant height. We just plug in our 10 for the radius and our 30 for the slant height, and we get all the way down to here where we get the exact value is 400 pi centimeters squared, which is approximately 1,256.6 square centimeters. Okay, in the second one, they're asking for the surface area of a cone again, but they make it a little bit harder this time because they don't actually give us the slant height. They give us the height. We're going to use that same formula, which is going to be pi r squared plus pi r slant height, but we need to calculate the slant height. So we use the Pythagorean theorem. This is a really important relationship in a cone. That right triangle is always formed with the height, the radius, and the slant height. And usually you'll have 2, and you'll just need to figure out the third. So we use our Pythagorean theorem, and we get our slant height here is 13. We put 13 into our formula for the lateral area there, and we end up with 90 pi, which is approximately 282.7 square centimeters. Okay, in problem 3, we're supposed to find the surface area of a paper cup. The diagram's not really clear here. I think 8 is meant to be a diameter of this cup, which means the radius is going to be 4. And again, because we need the slant height to find surface area, we're going to need to use the Pythagorean theorem. So we have a 4 radius, a height of 12, and the slant height we can find by using the Pythagorean theorem. Turns out to be about 12.6. Now, we don't need the top to this cup. We only need the lateral area. So we're going to do pi times r times the slant height. Slant height was 12.6, and that gives us about 158.3 square centimeters. And when they ask what assumptions you made here, the 158.3 centimeters squared would be perfect if we didn't have any overlap in the cup. Okay, for problem number 5, they only give us the lateral area and the radius, and they ask us to find the height and the slant height. So we use the formula for lateral area, which is pi r slant height, and we put in 60 for our lateral area, 4 for our radius, and then we use our number sense and algebra skills, dividing both sides by 4 pi to figure out that slant height is 4.77, and we still have some work to do. So now we got to calculate the height. We use this right triangle here where that's 4.77 for slant height, which is your hypotenuse, radius is 4, and we figure out the height this way. Our right Pythagorean theorem looks like this. H squared plus 16 is approximately 22.8, subtracting 16 from both sides, then square rooting both sides, we get the height is approximately 2.6. Okay, so number 6 here is a very good question. It asks, if you double the height, will that double the surface area of this thing? Now, intuitively, you guys should be able to figure out, well, if the circles that are the base are the same and the height is doubled, that doesn't really affect the area of the base. And so intuitively, you should probably say that that's not going to be the case. It's not going to double the surface area. But you could just try it with an example. So if I let that radius be 3 and that height be 4, then that radius would be 3 and that height would be 8. And you go through the process of finding the slant height. For this one is 8.5. The slant height for this one using the Pythagorean theorem will give you 5. And then you plug the numbers in, and here you end up with a surface area of 24 pi, and here you end up with one that's 34.5 pi square units, which is obviously not double 24 pi. Okay, so page 454 now. Problem 1b is looking for the volume of a cone. And volumes of a cone is just like volumes of pyramids, only better in some ways because the base is always a circle instead of a triangle or a square or other random sort of polygons. So you know that base area is always going to be pi r squared. So the only things you need for this volume are to find the radius, which is given to us, and the height, which is given to us. So you just plug it into that formula, and you get 188.3 cubic meters. So in this one, they're asking again for the volume, but they're making it a little bit harder for us because they're not giving us the height. Okay, so what they do is they give us the slant height and the radius. So again, with cones, we got to go back to our right triangle here, which is always the height, the radius, and the slant height. And using Pythagorean theorem, I can find out that the height is 1.7. Then I go into my volume formula, pi r squared h, put 1 in for the radius, 1.7 for the height, and I will get 1.78 cubic meters for the volume. Okay, in number 4, they give us a paper cup here, and they tell us the volume and the diameter, and they want us to find out the height. So my formula, volume equal pi r squared h, has 3 variables in it, but they give us 2 of them. They tell us the volume is 67, they tell us the diameter is 6, which makes the radius 3, and so that only leaves 1 variable left in our equation, and it's the one we're looking for. So we simplify that, we end up with 9 pi h. We solve equations by canceling out the 9 pi by dividing both sides by 9 pi, and we get a height of 2.4 centimeters. Okay, for problem number 5, they tell us that a cone fits perfectly inside a cylinder. Okay, well that's the thing about those formulas. The formula for volume of a cylinder and volume of a cone. If they have the exact same radius and they have the exact same height, then the volume of the cone is 1/3 of the volume of the cylinder. So we don't have to do much math here. We just know that if that's 300, this has got to be 1/3 of that. So that volume is also going to be 1/3 of 300 is 100. Okay, page 459. Now we're talking about spheres. Spheres are really great because you only have one variable that you ever have to worry about, and that's the radius. So for surface area of a sphere, it's going to be 4 pi r squared, and they tell us the radius is 6 centimeters. So we just put 6 in for r. That gives us exactly 144 pi, which is approximately 452.4 square centimeters of surface area. In number 3, this time they're giving us the surface area, and they're asking us to find the radius. And again, that's one of the things that makes a sphere great. There are only 2 variables in this equation, surface area and radius. So if they give us the surface area, all we got to use is our inverse operations to solve it. So how do I cancel out this 4 pi that's being multiplied? We divide both sides by 4 pi. I get 3.38. How do I cancel out the squared? I square root both sides, and I get the radius to be 1.8 meters. Okay, in number 4, we have a sphere that's actually a basketball. And we're trying to figure out how much it's going to cost for the leather to cover that basketball. Okay, well, we know that the diameter of the basketball is 24.8 centimeters, which means the radius is half of that, or 12.4 centimeters. So we put that into our formula for surface area, 4 times pi times 12.4 squared, and we get a surface area of 1,932.2 square centimeters. Now the problem is the cost they give us is cost per square meters. So I need to know that 1 square meter, which is 100 by 100 centimeters, is going to be 10,000 square centimeters. So now I take that 1,932, divide it by 10,000, and this is how many square meters of leather I'm going to need to cover that ball. Now that I have that, the cost of the leather is $28 for every square meter. So I multiply $28 times 0.19322, and that's going to give me $5.41 worth of leather to cover that ball. Okay, number 5, we're looking at the surface area of the Earth. So they tell us the diameter of the Earth is 12,800 kilometers, which means the radius is 6,400 kilometers. So we simply plug that into our formula, 4 pi 6,400 squared, and that is going to give me 514,718,540 square kilometers of surface area around the Earth. There's a little more than 7 billion people in the world, something like that, so that's probably about 10 people per square kilometer. That doesn't sound so crowded. There's that little matter of oceans and stuff, though. That's the problem. And the assumption we're making here is that the Earth is a perfect sphere in order to use our formula for a sphere. Okay, moving on to page 465, now we're dealing with the volume of a sphere, and it's really, the formula is slightly more complicated, 4/3 pi r cubed, but still it's only 2 variables, volume, radius. So if they tell us the radius, 14.2, we just plug that into our formula, and we get 11,994 cubic units. Okay, and number 3, we're talking about the volume of hailstones. Very interesting story there, but to actually find the volume is pretty straightforward, same as before. 4/3 pi r cubed. They tell us the radius of one of these hailstones was 8 centimeters. We plug 8 in for the radius, and we end up with 2,145 cubic centimeters of volume. Okay, number 4, last problem of the assignment. We have a sphere, spherical table tennis ball. So a sphere inside of a cube, all right? It fits perfectly inside the cube, and since the cube has an edge 40 millimeters, that means the radius of that sphere is going to be 20 millimeters. So again, for volume, we just put the 20 in for the radius, and we simplify that expression. So we end up with 33,510 cubic millimeters. The volume of the cube itself is just going to be side cubed, or length times width times height, 40 to the 3rd power, which is 64,000 cubic millimeters. And if you want to see how much space is actually wasted, all you have to do is take the volume of the cube, subtract the volume of the sphere. 64,000 minus 33,510 leaves us with 30,490 cubic millimeters of wasted space. Okay, I hope that answers any questions you guys had about this particular expectation. Next up is going to be application, so good luck with that, and I'll post some solutions to those at a later date.